Your engine is burning oil. Not a little, not a trace. A quart every 1,000 miles, sometimes every 800 miles. You check the dipstick on a Tuesday morning and it reads fine. You check it again 3 weeks later and it is sitting below the minimum line. No visible smoke, no warning light, no puddle under the car. The oil is just disappearing, and the engine is running it silently into the combustion chamber and burning it like fuel. You take it to a shop. They put it on the lift, do a leak-down test, pull some data, and come back with the estimate. Piston rings, carbon buildup, possible valve stem seal wear. The quote sits somewhere between $5,000 and $9,000 depending on what they find once the engine is apart. And they will remind you that those numbers can go up if the cylinder walls show scoring or if the head gasket decides to fail during reassembly. If you own a Subaru 2.5, a BMW N20 or N26 4-cylinder, an Audi 2.0 TFSI, a Toyota 2 ZRFE, or a GM 2.4 Ecotec, you probably already know this feeling. Consumer complaints filed with the NHTSA and documented class action lawsuits in the United States have identified oil consumption as one of the most common and least resolved issues across those platforms. BMW has stated in writing that consuming 1 quart every 750 miles can fall within acceptable limits. Audi has made similar statements. The manufacturers built a policy around what should have been unacceptable. And millions of American drivers are left managing a problem they were never told to expect when they signed the purchase agreement. Here is what almost nobody in the US market talks about. In Japan, independent mechanics have used a structured multi-stage chemical process for decades to address exactly this problem without dismantling the engine. No machine shop, no head removal, no piston pulling. A process that costs a few $100s in materials, takes a weekend, and in the right situation brings oil consumption from a quart every 1,000 miles down to nearly nothing. Today, I am walking you through exactly how this method works, stage by stage. But first, you need to understand the actual cause of the problem, because this method is not a universal fix. It works when the diagnosis is correct, and it fails when it is not. Understanding why your engine is consuming oil is the difference between solving a $300 problem and accidentally masking a $7,000 one. Why your engine is burning oil, and why the rings are almost never actually broken. Inside every piston in your engine, there are 3 rings. The top 2 are compression rings. Their job is to contain combustion pressure and prevent it from escaping down into the crankcase. The 3rd ring, positioned at the bottom of the piston, is the oil control ring. It typically consists of 2 thin rails held apart by an expander spring between them. Its entire purpose is mechanical and simple: to scrape excess oil off the cylinder wall on every downstroke and push it back through small holes in the piston into the crankcase below. When the oil control ring works correctly, only a microscopic film of oil stays on the cylinder wall for lubrication. That film is measured in microns. You cannot see it. It does not smoke. The engine burns essentially no oil between changes. That is how it is designed to work. Now here is where the problem begins. Over time, oil breaks down. Combustion byproducts, heat cycles, short trip driving where the engine never fully warms up, direct injection engines that produce more soot because fuel never contacts the intake valves. All of it creates varnish and carbon deposits. Those deposits accumulate in the ring grooves. The oil control ring loses its ability to move freely. It stops expanding outward against the cylinder wall. It stops scraping. It sits there partially stuck, and oil that should be returning to the crankcase instead gets dragged up into the combustion chamber and burned. Blue smoke on startup. Dipstick dropping between changes, the smell of burning oil in the exhaust on a cold morning. Here is the detail that changes everything, and the detail that most American repair shops skip entirely. In a high percentage of these cases, the rings are not physically worn out. The metal is still within factory tolerance. The clearances are still acceptable. The problem is not mechanical degradation. The problem is chemical contamination. Carbon has physically glued the oil control ring in place. It cannot move because it is cemented into the groove by hardened deposits. Japanese technicians identified this distinction decades ago. Instead of immediately recommending an engine rebuild for what is fundamentally a contamination problem, they developed a structured chemical process designed to dissolve that carbon and restore ring mobility. The goal is not to add something to the oil and hope for the best. It is a deliberate, staged procedure where each step prepares the engine for the next. Skip stages and you waste money. Rush the timing and you get incomplete results. Patience is the actual tool. Before you start, the compression test is mandatory. This is not optional and it is not overcautious. Before any chemical cleaning is attempted, every cylinder must be tested. A compression test at an independent shop in the US typically costs between $100 and $200. It is the single piece of information that tells you whether the chemical method has any chance of working. If all cylinders read within approximately 10% of each other and within the manufacturer's specified range, your engine is a strong candidate. The mechanical structure is intact. The rings are likely stuck, not broken. The chemical process has a real chance of freeing them. If one cylinder reads significantly lower than the others, or if there is wide variation across the set, the problem is structural. A solvent cannot restore lost metal. It cannot straighten a scored cylinder wall or replace a ring that has physically broken or lost spring tension. In that situation, the rebuild conversation is legitimate. Proceeding with chemical cleaning anyway wastes money and delays the inevitable. There is one additional scenario worth acknowledging. A small percentage of very high mileage engines with severe long-term neglect can develop a condition where accumulated carbon is actually helping to maintain compression by filling gaps created by wear. Removing that carbon in those specific cases may slightly reduce compression. It is uncommon, but a pre-treatment compression test is what tells you whether you are dealing with that situation. No guessing. Numbers first. Stage 1. Cleaning from the crankcase side. The process begins by attacking deposits from below. With the old oil still in the engine and the engine cold, add a professional-grade engine flush product. In the US market, Liqui Moly Engine Flush is one of the most commonly used products for this purpose. It contains a blend of solvents and detergents specifically formulated to loosen varnish, sludge, and early-stage carbon deposits from internal surfaces. With the flush added to the old oil, start the engine and let it idle. Do not rev the engine. Do not drive the vehicle. Idle only for 10 to 15 minutes. That is the window. Extended idling with a flush chemical added to the oil can accelerate wear if pushed past the recommended time. The goal is just enough dwell time for the chemistry to begin working on the lower ring pack and the piston drain back holes. After the idle period, drain the oil completely and replace the filter. What comes out will likely be darker and more contaminated than normal. That is the flush working. According to specialized engine shop documentation, approximately 60 to 70% of ring pack deposits accumulate on the underside of the piston and in the drain back holes. Cleaning from the crankcase side first loosens that material and makes the next stage significantly more effective. After draining, install a new filter and refill the engine with inexpensive conventional oil, not your premium full synthetic. This oil is a rinse medium. It will be drained again shortly, and its only job is to carry away any remaining loosened material during the next driving period. Stage 2. The pistons soak through the spark plug holes. This is the core of the Japanese method. This is what separates it from simply adding an additive to the crankcase and calling it done. This stage puts solvent in direct contact with the stuck ring through the top of the piston. Remove all spark plugs. Rotate the crankshaft manually using a wrench on the crank pulley bolt, until each piston sits at or near bottom dead center. This maximizes the volume in the cylinder and allows more solvent to contact the ring groove area. With each piston positioned correctly, introduce approximately 1 to 2 ounces of a high-solvency carbon dissolving product directly into each cylinder through the plug hole. In the United States market, B12 Chem Tool is one of the most commonly referenced products for this application. It contains xylene and petroleum distillates, which are aggressive enough to break down hardened carbon deposits, but generally safe for internal engine components when used within reasonable time windows. The goal is to flood the piston crown so the solvent migrates down around the ring lands and into the ring grooves where the stuck oil control ring is sitting. After introducing the solvent, loosely reinstall the spark plugs to slow evaporation. Do not tighten them fully, then leave the engine alone. Here is where most people fail because impatience is universal. Workshops in Japan recommend a minimum soak time of 12 to 24 hours. For more stubborn or longer-standing ring sticking, 48 hours is preferred. Every 8 to 12 hours during that soak period, manually rotate the crankshaft approximately a quarter turn. This shifts the solvent around the ring groove, exposes new contact surfaces, and allows deeper penetration into areas the initial fill might not have reached. During the soak, some solvent will migrate past the rings and into the crankcase. This is not a problem. It is actually confirmation that the solvent is traveling through the exact path that oil was taking when it was being burned. The chemistry is reaching the right location. The one step you cannot skip under any circumstances. After the full soak period, remove the spark plugs again. Place clean rags over each plug hole. Disconnect the fuel injectors or pull the fuel pump fuse and disable the ignition system. Then crank the engine for a few seconds without allowing it to start. This expels any remaining liquid sitting on top of the pistons. Do not skip this. Do not shorten it. If you allow the engine to fire with significant liquid sitting on a piston crown, you create a condition called hydrolock. Liquid does not compress. When the piston attempts to travel upward into a cylinder filled with liquid, the connecting rod absorbs the force. Connecting rods are designed for combustion loads. They are not designed to push against incompressible fluid. They bend, sometimes catastrophically. At that point, a chemical cleaning job becomes a destroyed engine block. Once you have cranked all remaining liquid out of the cylinders and confirmed the rags show no significant pooling, reinstall the spark plugs properly, restore fuel and ignition, and start the engine. The smoke that follows will be dramatic, dense, white to gray exhaust that makes it look like something has gone seriously wrong. Nothing has gone wrong. That smoke is dissolved carbon and solvent residue burning off. Let the engine idle until it settles, then take a gentle 15 to 20-minute drive. No hard acceleration, no high revs. After the drive, immediately drain the conventional rinse oil and replace the filter again. That oil is now carrying dissolved carbon and solvent residue throughout the lubrication system. It should not remain in service. Freeing the rings addresses the source of oil consumption, but if the top end of the engine remains coated in carbon deposits, the problem will gradually return. Deposits on intake valves, piston crowns, and combustion chamber walls create localized hotspots. Those hotspots raise temperatures unevenly, promote pre-ignition, and accelerate new carbon formation. The cycle restarts. Japanese workshops often use dedicated induction cleaning equipment. Systems like those produced by Waco's introduce a specialized cleaning solution directly into the intake manifold while the engine runs, creating a controlled internal cleaning effect on valve faces and combustion chamber surfaces. In the United States, the practical equivalent is an intake manifold cleaner spray introduced through a vacuum port on the intake. With the engine fully warm and held at approximately 2,000 revolutions per minute, introduce the cleaner slowly through a vacuum line. The operative word is slowly. Feed it gradually. The engine will begin to struggle as the cleaner enters the intake. Keep it on the edge of stalling without letting it stall completely. The stumbling is the process working. Once the product has been introduced, shut the engine off and allow it to soak against the hot combustion surfaces for about 15 minutes, then restart it. The exhaust output at this point will be intense. You will see dense, heavy smoke that looks far worse than what followed the piston soak. That is exactly what you want to see. Softened carbon leaving the combustion chamber through the exhaust. It is dramatic. It is completely normal. Let the engine run through it. Stage 4. PCV system inspection and replacement. This stage is the most overlooked part of the entire process, and the primary reason oil consumption returns for some drivers who complete the chemical cleaning but skip this step. The positive crankcase ventilation system manages pressure inside the crankcase by routing blow-by gases back into the intake to be burned. If the PCV valve sticks open, the crankcase develops excessive vacuum and draws oil past the rings directly into the combustion chamber. If it sticks closed, crankcase pressure builds and forces oil past gaskets and seals. Both failure modes produce measurable oil consumption. Neither one will be solved by cleaning the piston rings. Independent shop data across multiple platforms suggests that between 15 and 20% of oil consumption complaints are caused primarily by PCV system failure. That is not a small number. A PCV valve at a United States parts store typically costs between $10 and $40, depending on the vehicle. Replacement on most engines takes under 30 minutes. If your PCV system is the actual root cause and you spend the entire weekend on a 5-stage chemical process without touching it, consumption will return within a few months and you will have no idea why. Beyond the valve itself, inspect every hose and fitting in the system for cracking, softening, or restriction. On engines with integrated PCV systems built into the valve cover, check the internal baffle and any diaphragm components. Any disruption to the pressure balance of the system directly undermines the oil control you just restored through the piston soak. Stage 5. The final oil fill and monitoring protocol. The engine is now chemically cleaned, the rings are freed, the intake is clear, and the PCV system is functional. Now it gets proper protection. Fill the engine with a high-quality full synthetic oil in the exact viscosity grade specified by the manufacturer. Do not attempt to address residual consumption by moving to a thicker grade unless the manufacturer explicitly permits it. Thicker oil in an engine designed for a lighter grade can reduce flow to critical components at startup and actually accelerate wear in the parts you just cleaned. Some Japanese technicians add a mild detergent-based treatment to the first fill for approximately 500 miles to continue gradually dissolving any remaining trace deposits. After 500 to 800 miles, perform one final complete oil and filter change. This removes anything that survived the cleaning process and ensures the lubrication system is running on fresh, uncontaminated oil with a clean filter. From that point forward, monitor consumption carefully over the next 1,000 to 2,000 miles. In documented cases where the root cause was carbon-stuck rings on an engine with good compression, consumption frequently drops to near negligible levels within the first 500 miles. Engines that have been burning oil for longer or where deposits were more severe may require a second full treatment cycle. That is not a failure of the method. It is the method working against a more stubborn problem. Results, realistic expectations, and what this method cannot do. This process does not work on every engine in every situation. Understanding that from the beginning is what separates success from disappointment. Engines that respond best in the U.S. market include the Toyota 2ZR-FE found in the Corolla and Matrix, which was the subject of formal lawsuits over excessive oil consumption. The Subaru 2.5-liter Boxer engine also responds well because its horizontal layout promotes deposit accumulation when maintenance intervals are stretched. The GM 2.4 Ecotec in the Chevrolet Equinox and Malibu is well documented for stuck oil control rings. Certain Honda 2.4-liter four-cylinder engines in the Accord and Nissan VaiQ Series 5.6 engines also show strong response rates when the root cause is ring sticking rather than wear. Turbocharged BMW and Audi direct injection engines often benefit most significantly from the intake cleaning stage, where valve deposits can be severe enough to impair combustion efficiency beyond what ring cleaning alone addresses. What this method cannot do is restore metal that no longer exists. Scored cylinder walls, rings that have physically broken or lost spring tension, out of round bores, and damaged ringlands are mechanical problems. No chemistry addresses mechanical failure. The compression test before starting is what determines which situation you are in. That test is not a formality. It is the gateway to knowing whether this process has any rational chance of working in your engine. The financial comparison is straightforward. A complete engine teardown for ring replacement in the U.S. runs $5,000 to $10,000 or more on most platforms. A remanufactured engine in turbocharged or imported applications often costs more than that installed. The complete 5-stage chemical method, including all flush products, solvents, intake cleaner, PCV components, and 3 oil and filter changes, typically stays under $400 to $600 in materials when done at home. Even at a specialized shop willing to perform the process properly, the cost remains a fraction of a rebuild. The savings when this method works against the right root cause range from 80 to 90% of what the alternative would have cost. The maintenance habit that keeps it from returning. If the process restores normal oil consumption, that result is not permanent by default. The conditions that cause the problem, extended oil change intervals, incorrect viscosity, and constant short-trip driving that never fully warms the engine, will continue to exist if nothing changes about how the vehicle is maintained. This is the part the Japanese approach treats as non-negotiable. Use high-quality, full synthetic oil, changed at the manufacturer's interval or more frequently if driving qualifies as severe duty. The severe service classification in most U.S. owners' manuals covers frequent short trips under 5 miles, extended idling, stop-and-go urban driving, and temperature extremes. Many American commuters qualify without knowing it. The positive crankcase ventilation system should be inspected at every oil change, not just once. That valve costs $15 and takes minutes to check. Letting it go 2 years between inspections is what allows crankcase pressure to quietly undo everything the cleaning process achieved. In Japan, this kind of procedure is not considered a repair. It is considered scheduled maintenance. Some shops recommend lighter versions of the first 2 stages every 20,000 to 30,000 miles as a preventive measure, long before consumption becomes noticeable. The philosophy is not to fix a problem once it is severe. It is to prevent it from becoming severe in the first place. That mindset is why properly maintained Japanese engines routinely pass 200,000 and even 300,000 miles with clean internals and stable oil consumption. Not because the engines are made of different materials, but because the maintenance culture treats carbon as something to be continuously managed rather than something to be ignored until it requires a rebuild. If your engine is consuming oil right now, you have a structured, documented alternative to consider before signing off on a $7,000 teardown. Run the compression test first. If the numbers are solid, the rings are likely stuck, not broken. Stuck rings respond to chemistry, not miracles, not marketing. Applied chemistry, applied patiently, in the correct sequence. That is the method. That is why it works. And that is why it costs a fraction of what most shops will quote you for the same outcome. If you want more breakdowns on diagnosing engine problems before they become expensive repairs, subscribe. The next video covers how to read a compression test correctly and determine exactly when chemical cleaning is the right call versus when the engine genuinely needs to come apart.